Hi there, and welcome to this lesson on Further Pure Mathematics 2. And in this lesson, we're looking at how you can use a substitution to convert a first-order differential equation that we can't solve into a form that we do know how to solve. Now, there isn't really any new theory, but these questions are quite long, quite difficult. We will go straight into an example. So example 1 says, so that the substitution u equals y minus x can transform the differential equation dy by dx equals y minus x plus 2 over y minus x plus 3 into du by dx equals minus 1 over u plus 3. And you'll notice we start off with the differential equation that we couldn't solve using any of the methods we've learned up to now. But by using this substitution, we're able to transform it into a differential equation in u and x, so the y and the dy by dx's get changed. And this differential equation we can solve by normal methods. So first step is using the substitution to change this differential equation into this one. Once we've done that, we'll then need to find the general solution of this differential equation. Once we've done that, we'll need to undo the substitution so that we have an equation which is in x and y. And then last of all, once we've done that, we'll then need to find the particular solution when x equals 1 and y equals 1. And we've been told the general form that that will have, where you have to find p, q, and r, which are all constants. Now, as I say, it's quite long, this question, and a little complicated at times, especially the first bit. But I'll let you have a go yourself first. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look at this. So we're using the substitution u equals y minus x. Now it's a little bit easier if we immediately rearrange that into y equals u plus x. And then once we've done that, what we'll do is differentiate both sides with respect to x. So differentiating y with respect to x gives us that. Differentiating u with respect to x gives us that. And if you differentiate x with respect to x, you get 1. Now, this next line, dy by dx is equal to u plus 2 over u plus 3. How do we know that? Well, if we have a look up here, dy by dx is equal to y minus x plus 2 over y minus x plus 3. But our substitution was that u is equal to y minus x. So y minus x on the top becomes u, y minus x on the bottom also becomes u. Now we've got an equation which has u's in and du by dx's, but we still can't solve this differential equation. We just need to do a little bit of work on it first. So moving the du by dx over to this side and the fraction over to that side, and then using partial fractions to combine these two parts together. So we'll have u plus 2 over u plus 3 minus u plus 3 over u plus 3. And when we add those together, that does give us minus 1 over u plus 3, which we were told in the question we should get. So that's the first step. What we've done is we've converted this differential equation into a form which we can solve. And the way we'll solve this one is by separating the variables. So bringing the u plus 3 over to the left-hand side and leaving the minus 1 over there, we'll get the integral of u plus 3 du is equal to the integral of minus 1 dx. Integrating that with respect to u gives us a half u squared plus 3u. Integrating minus 1 with respect to x gives us minus x, and we do need to add an arbitrary constant. Now we'll undo the substitution. So right back at the beginning, we were given a substitution u equals y minus x. And so we'll substitute y minus x in for u. That gives us this, and that can be tidied up to give us a half y minus x squared plus 3y minus 2x plus 3 equals 0, is the general solution of the differential equation. But there's still more work to do, because we've been asked to find a particular solution when x equals 1 and y equals 1. Well, that's fairly straightforward to do. All we have to do is substitute those two values into the general solution. And when we substitute those values in, we will get this, which tidies up to give us c equals -1. So substituting c equals -1 into the general solution gives us the particular solution of this differential equation. Oh yes, and the question asks us to find P, Q, and R explicitly. So P will be equal to 3, Q will be equal to -2, and R will be equal to -1. Okay, example 2. Show that the substitution y equals ux transforms the differential equation, given there, into an easier one, x du by dx equals 4 plus u squared. And then we're asked to find the particular solution, given that when x equals 1, y equals 2. Okay, once again, I'll let you have a go at doing this yourself first. So pause the video, have a go, and then come back to me again when you're ready. Okay, let's have a look. So this time the substitution is y equals ux. Now the easiest thing to do this time is just to differentiate it straight away. So differentiating the left-hand side with respect to x gives us dy by dx. And we'll need to use the product rule to differentiate the right-hand side. So writing down the u and differentiating x gives us the first term. Writing down x and differentiating the u gives us the second term. Then we substitute for y and dy by dx in the original differential equation. So where it says y, we're going to substitute in ux. Where it says dy by dx, we're going to substitute in this function in u and x. And when we substitute those in, that is what we get. Tidying that up will give us this, and tidying it up even more gives us that, which is what we were asked to prove it was equal to in the question. So all is well. And this we can integrate by separating the variables again. So we'll get 1 over 4 plus u squared du, the integral of that, is equal to the integral of 1 over x dx. Now, the integral on the left-hand side, it's the same, and the reason why I've rewritten it will become clear in a minute. It's the same as a quarter into the integral of 1 over 1 plus u over 2 squared du. And the reason why I've written it in that form is because that is a standard integral. Now, you should have a sheet, a formula book, which has all standard integrals on that you're not expected to know and remember, but you are expected to be able to refer to in the exam. If you do learn them, all the better. But you wouldn't need to learn this one. And that's the standard integral there, that the integral of 1 over 1 plus x squared dx is equal to the inverse tangent of x. And this integral has exactly that form, where x is equal to u over 2. So if we integrate the left-hand side of this, we'll get a half times by the inverse tangent of u over 2. And the reason why the quarter is changed into a half is because if I differentiated that, I would get the 1 over 1 plus u over 2 squared, but then using the chain rule, when I differentiate the u over 2, I get times by a half, which will give me the quarter that I need. On the right-hand side, things are a lot more straightforward. Integrating 1 over x is log x plus a constant. Now we need to undo the substitution, y equals ux. That means that u is equal to y divided by x, and we'll substitute that in for u here, which gives us half times by the inverse tangent of y over 2x is equal to log x plus c. That's what we just did. Now then, the particular solution that we're asked to find is the one where x equals 1 and y equals 2. Now, if I put y equals 2 in here, I'll get 2 on the top. X equals 1, I'll get 2 on the bottom. 2 divided by 2 is where that 1 comes from. And then the log of x is the log of 1. And the inverse tangent of 1 is pi by 4 radians. The log of 1 is 0. So that gives us c is equal to pi by 8, which we can substitute back into here to give us a half times by the inverse tangent of y over 2x is equal to log x plus pi by 8. Now, the reason why we're carrying on is when we find the solution, strictly speaking, we really want to get y written as a function in terms of x. It isn't always essential, but it is the normal thing to do. So multiplying the equation by 2 has given me that. And then I take the tangent of both sides. Taking the tangent of the left-hand side, then tangent cancels with inverse tangent. And taking the tangent of the right-hand side will give me that. Then all I need to do is move the 2x over to the other side, and I've got y written as a function of x. So that is the particular solution, y equals 2x times by the tangent of pi by 4 plus 2 log x. Okay, one more example. Have a go at solving dy by dx equals 2y over x plus 2x times by the square root of y, where x is bigger than or equal to 1 and y of 1 is equal to 0. And we'll be using the substitution y equals u squared. I'll let you have a go, pause the video, come back to me when you're ready. Okay, let's have a look. Y equals u squared is the substitution. If I differentiate both sides of that, I get dy by dx on the left-hand side. And using the chain rule, I get 2 times u, and then du by dx when I differentiate the u. Substituting for y and dy by dx in the original equation will give me 2u times by du dx equals 2u squared over x plus 2xu. And tidying that up gives me du by dx equals u over x plus x, which means du by dx minus 1 over x times by u equals x. And the reason why I've written it in that form is it becomes slightly clearer then that this is the form of equation that we can use an integrating factor to solve. So this now has the form dy by dx plus p times u equals q, where p and q are both functions of x, p is minus 1 over x, and q is just x. So that's where we've got so far. And the integrating factor will be e to the integral of p, which is e to the integral of minus 1 over x. The integral of minus 1 over x is minus log x, which is e to the power of log x to the power of minus 1, using the law for logarithms. And the reason for doing that is e and log are inverse functions, so they cancel each other out. And the integrating factor is just x to the minus 1, or 1 over x. Now we multiply by 1 over x, and that will give us 1 over x du by dx minus u over x squared is equal to 1, which is where we've got to there. And that means that d by dx of u over x is equal to 1. So combining these two terms into one single differential. Then we integrate both sides with respect to x. Integrating the left-hand side gives us u over x. Integrating the right-hand side gives us x plus c, which means u is equal to x times by x plus c. Now we need to undo the substitution. Well, the substitution was y equals u squared. The easiest way to undo this substitution is change this to u squared. So squaring the left-hand side gives us u squared, squaring the right-hand side gives us that, and then we can just substitute y for u squared, which means that the general solution is y equals x squared times by x plus c squared. Now the last thing that we have to do is find the particular solution given by y of 1 equals 0. So that is the initial condition, and what it means is that y equals 0 when x equals 1. You may not have seen this notation before, but that's the way you would read that. So y when x equals 1 is equal to 0 is the way you would read that. Substituting those in gives us 0 equals 1 squared into 1 plus c all squared, which gives us c equals minus 1. which is the only solution to that equation, which means that the particular solution is y equals x squared times by x minus 1 squared. Okay, that gets us to the end of this lesson. If you've got the textbook, then turn to page 101 and have a go at exercise 5C. Thank you very much for listening, and cheerio.